In this video, we're going to be looking at how to apply proportional reasoning to Kepler's second law, Kepler's third law, and to Newton's law of universal gravitation. Starting off, we have this question here where it says we have an object moving at a speed of 90 kilometers per hour when it's a distance of 0.5 astronomical units from a star. Then it asks us, what is its speed when it's 3 astronomical units away? And it wants us to give this answer in terms of our initial speed. So starting off, we have some key information, initial conditions. We have 90 kilometers per hour, and it is 0.5 astronomical units from a star. And then it's asking, what is the speed when it is 3 astronomical units away? And it wants this in terms of the initial speed. Now, if we have no external torques, we know that we're going to have conservation of angular momentum. So our starting angular momentum is going to be equal to our final angular momentum. And the way that we can write out angular momentum is momentum multiplied with the distance from the axis of rotation. So we're going to call that r. And we're going to have that on both sides. So momentum multiplied by the distance from that axis of rotation. Now this is going to be the same mass. I'm going to put these as m1. Now we're going to have an initial velocity and then a second velocity, that final velocity when it's at a different distance. So I'm going to call these distances r1 and r2 respectively as well. Now if we look on both sides of our equation, we have m1. So if I were to divide both sides by m1, they're going to cancel out. They will both become 1. And then if I divide both sides by that second distance from our axis of rotation, we will have our equation. So our equation that we're going to use is this new velocity is equal to our initial velocity multiplied with our initial distance divided by our new distance. I made a mistake. That should be r1 divided by r2. And now what I'm going to do is I'm going to plug this into Desmos, but let me write out all my values. So V1 is actually 90 kilometers per hour. So this is going to be 90 kilometers per hour. R1 was going to be 0.5 astronomical units. R2 is 3 astronomical units. And if I look, my astronomical units are going to cancel out because they have them on top and bottom, meaning that my answer is going to be in terms of kilometers per hour. Now I'm going to come to Desmos and just type in what I see. So I have 90 multiplied with 0.5. This whole thing is going to be divided by 3. And this tells me that my answer is going to be 15 kilometers per hour. That is my answer. But it's asking me to give my answer in terms of the initial speed. So the way that I do this is I set up an equation where I have my final velocity is equal to some ratio of my initial velocity. And the way we do this is we take our final velocity and we put it on top of our initial velocity. So this is going to be 15 divided by 90. So in terms of our initial velocity, this is going to be, now I could see that I have repeating 6's right here. I'm just going to round that first 6 to a 7 because this is 5 or greater. I'm going to put 0.17. This is telling me that my final velocity is equal to about 0.17 of my initial velocity. So if I took this initial velocity of 90 and I multiplied it by 0.17, I'm going to get something really close to 15. Now let's try this. 0.17 multiplied with 90 gives us 15.3. We get this little rounding error because I rounded here. Okay, let's take a look at the next problem. Okay, so the next problem is talking about Kepler's third law. And remember, Kepler's third law tells us that for all bodies orbiting the same central body, we're going to have this thing called Kepler's constant that remains the same number for all of these orbiting bodies. And it tells us that we have a proportionality between the square of our period and the cube of our radius. Sometimes you'll see it as A. I'm going to use R for this one, but it says two objects orbit the same star. The first object is 1 astronomical unit away and has a period of t. The second object is 9 astronomical units away, and it's asking in terms of that initial period, what is the period of the second object? So in terms of t, meaning that period of the first object, we want to know the period of the second object. What that tells me is I want to get period by itself. I want to get rid of this exponent right here, so I am going to square root both sides. If I square root both sides, it's going to remove this exponent, and that's the equation that I'm going to use. This is my initial condition right here. Okay, so that new period is going to be this equation. So it's my original conditions, but now with this new change. So I went from 1 astronomical unit, and now I'm at 9 astronomical units. So I could set it up the same way that I did before. I'm now at 9. I used to be at 1. Okay, so these are my changes. All the numbers that I just plugged in, those are my changes. I want to pull those out. So I'm going to put my new period is going to be square root. 9 divided by 1 is 9. I'm going to keep the cube that we see right here that was attached to the r. And this, everything inside of here is now square root r cubed. And I could see that anytime I have this right here, anytime I see this, it's the same thing as my initial period. So what I'm going to do is I'm going to replace this. I'm going to put this as the original period. Okay, so I'm going to come over to Desmos and put SQRT, and now this is going to be 9 cubed, and this tells me that it's going to be 27 times greater than my original period. So the period is now 27 times greater. What this tells me is if we're looking at Earth and I can see that, so I have something that is 9 times the distance of Earth, it is going to take 27 years to complete one complete revolution around the sun. So the new period is 27 times whatever my original period was. All right, so let's take a look at the next question. All right, so the next question is another Kepler's third law question. This time it's telling us that it wants us to give our answer in terms of radius. So 2 objects orbit the same star. That's great. It tells us that they are going to share the same Kepler's constant. The first object has a period of 1 year and is 1 astronomical unit away. The other object has a period of 8 years, and it's telling us in terms of the first object's distance, what is the distance of the second object? So again, we're going to start off with just what we know. We know that our period squared is going to be proportional to the cube of the distance, that average distance between the central body and our orbiting object. Now, since we're giving our answer in terms of distance, I need to get this r by itself. So now I'm going to do the cube root. This is going to be cube root. I'm going to cube root both sides. This turns into just the r. So anytime I see the cube root of t squared with no other numbers in it, that's equal to my original radius. Now what I'm going to do is I'm going to put the new distance, and this is going to be equal to, I got to plug in my changes, so the cube root of t squared, but I have a number that I'm going to attach to. Another object has a period of 8 years, and it used to be 1 year. So this is going to be 8 over 1. Again, just like I did last time, I'm going to pull out all those numbers that I just wrote down. So the new radius is going to be the cube root of 8 squared multiplied with the cube root of t squared. Now when I see the cube root of t squared, that is the same thing as my old radius. So because I have this right here, I could actually substitute that into what I see here. That is going to be how I solve this. So this is going to be my original radius. Now I'm going to come over to Desmos. I'm going to put CBRT, cube root, and this is going to be 8 squared, and I get 4. So my answer here is going to be, my new radius is 4 times the old radius. Okay, so let's take a look at the last type of question. So this one will be concerning Newton's law of universal gravitation. and let's read over it. Okay, Newton's law of universal gravitation. The gravitational force between two objects is F. When one object has a mass m and the other has a mass capital M, they are 2 astronomical units apart. How does the force compare if one object's mass is doubled, the other object's mass is halved, and the distance is 4 times? And we want to give our answer in terms of that initial force. Now, our equation that we have here, so Newton's law of universal gravitation is that our force from gravity is equal to the gravitational constant of 6.67 times 10 to the negative 11 multiplied with our masses. I'm going to put a big M and a small m just like they have in our question over the distance squared. Now, just in case we've forgotten, I'm going to show you how we could actually model our force. So I know that my force as a function, so my force as a function of my distance called r is going to be equal to 1 over, so I'm just replacing everything with a 1. I'm going to just say that this isn't changing, this isn't changing, this isn't changing. So I'm looking at what happens when my radius changes. So I'm just looking at this variable and this variable. And then I'm going to call this r, and I'm going to square it. So this is the relationship. This is how we can model a relationship. This tells me my force as a function of the radius, so the distance. And I can see that as my distance increases, my force is decreasing dramatically. And I could actually do this with any of my variables. So I could put, if I wanted to look at what happens with the mass, so that big M, I could just put a big M over here. And this would be over 1 because I'm replacing everything else with 1. And I can see that this is actually a linear relationship. And I get the same relationship with small m. The gravitational constant doesn't change. So the big thing that I could see here is that my force decreases significantly. It actually decreases exponentially as my distance increases. Okay, so I'm going to set this up as this is my original force right here. And now I'm going to write out my new force. So my new force, let's put it in black so everything stands out a little bit more. So my new force is going to be the same equation. G never changes. We have big M, we have little m over r squared. Now I want to plug in my changes. Okay, so it says the gravitational force between two objects is F when one object has a mass of m, the other has a big M. They are 2 astronomical units away. All right, so I could see that my astronomical units, it gave me a value and it changed. So what I want to do is first I'm going to plug in what I could see here. So it's now 4, it used to be 2. How does the force compare if one object's mass is doubled? So I'm going to just say that this one doubled and the others is halved. Okay, and then we can see that the distance is now 4. It used to be 2. Everything I just wrote in red, I'm going to pull to the outside. Okay, so my new force, actually let me keep that other part in so you can see it. So remember, anytime I see GMM over r squared by itself, that's just my original force. Okay, so I'm going to put my new force is equal to, then I'm going to write down everything I have in red. So this is going to be 2 times 1/2 over 4 over 2. This has to be squared. And then I'm going to have my original equation. So G big M little m over r squared. Everything I see right here, I can substitute this into it. So I'm going to substitute in the original force. So this all becomes the original force. So this is my original force called Fg. And now I'm going to use Desmos to actually do all the math for me. So I could see that I have a fraction, so I'm going to start off the fraction. Then in my numerator, I'm going to have 2 multiplied with 1/2. And then on the bottom, I'm going to set up parentheses. So I could put 4 over 2. And I'm going to square this. And it tells me that my new force is going to be about 1/4 of my original force. So this is going to be 0.25 of what my original force was. And that's all you have to do with proportional reasoning. We're just showing our new force in terms of our old force. If I wanted to show my old force in terms of my new force, I would divide both sides by 0.25. And it would give me the same relationship, just in a different perspective. It would give us in respect to our old or our new force. Okay, that's it.